Hello, everyone, and welcome to the SciRoc camp. Hi there, my name is Deebul, and I'll be your host and moderator for the SciRoc camp. I'm the coordinator of the European Robotics League Professional Service Robot under the SciRoc project. And as the host, I'd like to welcome and invite all our audience from joining us from the different parts of the world in this live webinar. So, what is the SciRoc camp all about? Let's have a small look. The SciRoc camp is an effort under the SciRoc project to train and develop new robotics team for participating in different robotics competitions and benchmark. It is also an opportunity to bring together the current robotics team in the community under a common roof and to share the ideas with the larger community. Last year, we made a significant impact in the robotics community with a successful event of the first Smart City event. It was held in Milton Keynes. It saw the coming together of three different distinct robotics communities: the Consumer League, the Professional League, and the Emergency League. And they were competing under one single environment in the Smart Cities setup. We would like to ride on the success and expand the reach of the competition to a larger community. And in order to boost this community building event, we have come with a week-long plan where we invite different with different teams and different research places to come and share their experience. Now, to introduce about the SciRoc project and to give the welcome speech, I would like to invite the SciRoc program coordinator, Professor Dr. Matthew Studley.
The Gerhard Kretschmer Memorial Symposium and SciRoc Camp. My name's Matthew Studley. I'm the coordinator of the SciRoc project, which is funded under the European Union's Horizon 2020 programme. Now, the reason why we're all here, of course, is because of the unfortunate death last year of our friend Gerhard after a long and protracted illness. Amongst his many roles, Gerhard was the Professor for Autonomous Systems at BRSU, a role which he'd held for many years. Indeed, Gerhard had been involved in robotics for a long time, taking his PhD in distributed reasoning back in 1996. Within the SciRoc project, Gerhard was the leader of ERL Industrial, which we have later named ERL Professional. And I have to say that Gerhard was a thoroughly nice guy. He was the sort of person you'd want to sit next to at dinner. A good conversationalist, very warm-hearted, very kind, and a very fine colleague with an extremely good intellect, the sort of person who sees solutions to problems that nobody else would think of, and indeed who understands that the problems exist before anybody else notices them. So he'll be greatly missed both as a colleague and as a friend. So the SciRoc project then. You'll be familiar with the European Robotics League, which benchmarks robots through competition. But often these competitions take place hidden away from the public. What we want to do is to bring robot competitions into the smart city. By 2050, it's estimated that about 70% of the world's population will live in cities, and increasingly these cities are becoming smart cities. That means that they have sensing, where they can sense their environment. They have processing, which could be distributed and associated with services and applications, or it could be centralized within the city itself in order to make decisions based upon this data. And of course, they take actions and change their environment. And if we think about this ecosystem of services and applications and the city itself as a whole, then it seems to be like one large robot. Why do we want to take robots and robot competitions into the center of the smart city? Well, because we want to be able to test these robots, benchmark them, but also demonstrate them to the public. And the main reason for this, and for doing it in the center of the city, is to stimulate discussion, because the technologies which you're developing will have an enormous impact on everybody's lives. And we need to ask the question, and members of the public need to ask the question, what sort of future do we want? Because these technologies have the ability to perform wonders or to make our lives thoroughly miserable. So we need to take control of this, and we need to engage the public in making these decisions. And the best way to do that is to equip them with facts about the real state of the art. So in 2019, we did our first SciRoc Smart City event, which was in Milton Keynes in the UK, and it was a tremendous success. We had many hundreds of thousands of people in attendance. It was outstanding. I'd like to show you a short video of that now, if I may. So you've got a lot of excitement lined up over the next few days. There's both the camp full of educational opportunities and equally the symposium, which has a number of presentations from esteemed colleagues from the discipline of robotics. And I'd like to finish up by saying, well, hopefully we'll see you in Bologna, because we're going to have a second Smart City event. More details of this to follow. Thank you, and I hope you have a good week.
Thank you, Matthew, for the welcome speech, and all the participants who are planning to join us in Bologna. I think this is a great opportunity to join in an international event. Now, Matthew had provided you a brief overview of the week. Let me give you a detailed version of the SciRoc camp. So we have a whole list of speakers running the whole week. The easy thing is the whole week, it's starting at 14 at Central European Time, summer. And so today we have the Campions talk series. And we have the team SocRob and team Bitbots, who will be giving the Campions talk tomorrow. At the same time at 14, we have the perception tutorial. And then on Wednesday, we have the planning tutorial by Oscar Lima. And on Thursday, we again end with the Campions talk, which had won this in the Smart City competition, the Bitbots at Home team. So this now sets up to our first talk, the introductory talk for our session. So the first talk is by team SocRob. So they are a team from Instituto Superior Tecnio University, Lisbon, Portugal, in the Institute for Systems and Robotics. Team SocRob has been participating in robotics competitions and benchmarking from 1998. They started from the Middle Soccer League, then moved to the domestic robots, and also have been active in emergency the league. So they have an experience of more than 20 years. I think this gives us more than an experience to more than a reason to listen to this whole experience from this team, which has gathered over this long year. So from the team, we have been joined by the team leader itself, Rui Bettencourt, who is joining us today to give the talk. So let's welcome Rui. Hi, Rui. I think you're muted.
Oh, sorry.
Yes.
Hi, Deepu.
Hello, and welcome to the SciRoc camp.
Thank you.
So I wanted to ask you, what do you feel about, what are your feelings about the SciRoc camp, and what are your expectations from it?
I think it's a great idea. I think it's going to be a very interesting week full of interesting talks. And once again, I want to thank you for the invitation, and I hope everyone enjoys these talks.
Thank you. So Rui was, so for the audience, so Rui was kind enough to provide us with a video recording. So the format of the talk is this way. So now we will watch the talk, which is provided by Rui, and later I'll be joined again by Rui so that we can ask him the questions. So for all your audience, you can ask him any questions, and all the I think this should opportunity be taken by all the teams who wants to join the SciRoc and the different robotics competitions to ask them any questions. So there are two formats in which you can ask questions. The first format is in the YouTube comment section. So you can comment there and we will ask Rui about it. The second is on the event website. So if you go to the SciRoc Camp website, you can also find a portal where you can add your questions in there. And please do ask questions. This is the right moment to connect with such a esteemed guest in there. So by saying this, I think I should move out and just enjoy and learn from Team SocRob.
Hello, my name is Rui Bettencourt, and I will be giving a talk on best practices and lessons learned in robotic competitions as part of SocRob Home team. The team is part of the Institute for Systems and Robotics, which was founded in 1992 and is part of Técnico Lisboa, an engineering university in Lisbon, Portugal. This institute has over 100 researchers, which include faculty members, research fellows, postdoc researchers, postgraduates, and undergraduates. It has 5 subgroups which tackle different areas, and one of them is IRSG, which stands for Intelligent Robots and Systems Group. This group focuses mainly on unmanned ground vehicles, or UGVs, and we approach the robotic system in an holistic standpoint rather than just focusing on a single robotics subsystem. We also try to approach problems that are challenging and pertinent, but also useful for everyone's daily lives. For example, home robots for service in people's homes, firefighting robots, rescue robots, and so on. The group also has more than 20 years of experience in robotic competitions, such as RoboCup or ERL. And the first competition that the team actually participated was in the Paris RoboCup in the soccer domain in 1998. And then the team's name met Soccer Robots because this was the domain that the team participated. The team was founded because we believe that scientific competitions help to address pertinent problems that can arise when we deploy these robots in the real world. In 2006, this team branched out to other domains, such as the rescue domain, under the name SocRob at Rescue. And this name SocRob now doesn't mean soccer robots, because we address other domains, but instead it means society of robots. In these 2 pictures, we can see one of the first years in competitions in the soccer domain. On the right, one of the first years. Well, actually, no, it's a more recent photo of the rescue domain, but you can see that it uses other kind of robots. The home domain started in 2014 for us. The team started to approach this domain under the name SocRob Home, and the goal was the same as the other domains, to advance the state-of-the-art in robotics, in this case in service robotics, by participating in robotic competitions. The team is formed by master students, PhD students, research engineers, and it's supervised by faculty members. Currently, we are supervised by 1 faculty member. We have 1 PhD student, 1 research engineer, 4 master students working on their thesis, and are responsible for the hardware. The project uses the M-Bot robots, which were made from the company ID Mind within the Monarch FP7 project. These robots were originally built to help autistic children in the hospitals, but were then upgraded to handle the more challenging home environment. More computing power was introduced to them, a manipulator that could actually do something, and so on. We can see in these pictures the robots, but also our test bed in our university where we do our tests. Then, who am I? I joined this team in February 2019. And in that same month, I had my first robotic competitions experience as a referee in the local ERL Consumer Lisbon. Then, as a more experienced member of the team, I participated in September in the ERL Smart Cities in Milton Keynes, in the United Kingdom. Here I was responsible for the navigation component of the robot. You can see on the left picture our team working in this competition. And then in November, I finished my thesis. I started working in the team as well, but as a research engineer. And then in January, I became team leader. In this year, we haven't been in any competition due to coronavirus, but in another team, I participated in the Mohammed bin Zayed International Robots Competition in the United Arab Emirates in February. This team was made by people from our group, but also from University of Seville and Catec Seville. And this competition meant to bring advancements in the cooperation between drones and UGVs. And it had 3 challenges. We won one of them, which was the firefighting challenge, where the robots had to cooperate and find the fires and put them out. Like I said, we won, and in the right we have a picture of the celebrations. Then I would like to motivate this talk by asking the question, why are competitions important? Why do people do them? Why do I do it after a year and a half? Why do some people do it after decades? For me, it comes out to these 4 points. Teamwork towards the goal, because you are not working alone when you are working in these competitions. You are working in a team, and you share interests, you share a common goal, and this will help you to bring the most out of your research. Then we also have cooperation between teams. These competitions, one of the biggest factor is that it has a lot of people from different backgrounds with different experience, but they all share the same goal. And you get to talk with all these people about robotics, and that is a very valuable experience. We also have public awareness. One way or another, these competitions are a lot to show the people what robots can do nowadays, what are the advancements we are producing, what are their tax-paying money being applied to. And although not all competitions have live audience, most of them have at least social media coverage, so one way or another people get to see what we are doing. The ones that have live audience have the special bonus of you can see what the people think of what you are doing. You can see their reaction to your research, and that is very valuable to me. The final point, but definitely not the least important, is the actual research you produce. In these competitions, there's usually challenging problems that are very challenging and pertinent to the advancement of this field. And usually these challenges have something that should be improved. And you get to see what several teams do about it, and you can end up with one or more solutions that you didn't have before for these problems. Then I will now give a small overview of our team. First of all, the hardware. Like I said, we use the MBot robot. This robot weighs around 25 kilos and has a maximum speed of 2.5 meters per second. And we can divide it mainly on the head and the body. The head is pan controlled, so it has a motor on the neck that allows it to rotate the head. This gives a bigger field of view. It also had a LED panel in the face to express emotions for human-robot interaction, and a camera on the head, a depth camera, which is tilt controlled to improve even further the field of view. So the robot has almost the field of view of a human. He can rotate the head and go up and down. So basically the field of view of a human. And there's also a microphone to detect people's voices. The body has a touchscreen for an extra human-robot interface if there's a need to. It has 4 Mecanum omnidirectional wheels that allow it to go anywhere. I'm sorry, that allow it to go in any direction. This is very good for tight indoor environments, which is the environments we use, and it allows it better mobility. The robot is also equipped with the siphon arm that has 7 degrees of freedom, but is not very robust or accurate. So we are in the process of replacing the arm It's not finished yet, but it will be soon. The robot also has 2 laser scanners, one in the front and one in the back to help with the navigation. And for computing, it has an Intel i7 and an NVIDIA GPU. As of the software, we are using Ubuntu 16, mainly because we use ROS Kinetic. ROS Kinetic has been a stable version for some years now. It's closing down on its end of life, but there are new distributions such as the Rosnoetic or even ROS2 that we will soon have to work on. But for now, we are using ROS Kinetic. This means that we have to use either Python 2.7 or C++. With the Rosnoetic or ROS2, we can use Python 3. That will be better, but for now, we are limited to this. And with these frameworks and programming languages, we can use the components to solve our problems. And we use some ROS packages available online, adapted to our case, in a combination with original solutions that we program to solve the problems we have. We can see our robot system as a system that interacts with people and its environment, and we can divide its main components. I usually divide in these, in the human-robot interaction to interact with the people, and then perception, manipulation, and navigation to interact with the environment, and then task planning to bring these all together and solve a specific problem. We can see one by one. First of all, human-robot interaction. We have the communication with humans. First, what they say is processed through the natural language processing we have, which is basically built with a Google automatic speech recognition, combined with the BERT-based natural language unit that a previous member built, and it's quite accurate. Then, after understanding what the people said and getting a response, we have to say it, and the robot uses his speakers and a text-to-speech, a normal text-to-speech, to say the answer to the person. Then it's also important to consider the body language of the robot in these human-robot interactions. First of all, when the robot is doing something related to a human, he should be human aware in its navigation, so its movements should consider the humans. Also, the emotions of the robot, in our case, it's easy because we have a LED panel, but it helps to have a robot with emotions so people understand if they are doing a good job or not in the cooperation with the robot. So all this body language of the robot is also important, and we have a special attention to this when we are doing our state machines. Then we also have perception, which is very important. We have, first of all, a detector. Actually, we have 2 detectors, a more general and a more specific one. Both of them run darknet YOLO models. So our general detector detects general things, as the name says. So it detects people, it detects general furniture like chairs, tables, TVs, beds, these kind of objects always appear in our competitions. And then we have a specific detector, which we train for each competition according to which set of objects we have to detect. Then, after detecting, we also need to track these objects to see where they are over time. And we have two trackers that we built using Bayesian filters, one for people and one for objects. In my opinion, the people one is more important, especially for people following tasks, but of course, both of them are very important. Then we also have a semantic map, which provides a geometric and a semantic representation of the world. And in this video, you can see our robot performing a small semantic map test where it has to find 3 objects, Pringles, a mug, and a Coca-Cola. And it goes around in several predefined locations, and it tries to detect. In this bottom right image, it's what he sees, and you can see here that he saw a Coca-Cola, and then he updates the belief of what he sees in each locations and where the objects are in a probabilistic model. Then we also have our manipulation. Our manipulation, in this case with the cyclone arm, uses an optomap to prevent collisions with furniture or other objects. This optomap is built using the depth camera. So he builds a 3D map of the environment with what he sees, and when the motion planning of the arm is calculated, it avoids these structures. Then he detects the object, he calculates the grass pose, and we use a Move It framework to calculate the motion planning. This is a ROS framework. Then we also use a position-based visual surveying to react to changes in the object. So if you change the object a bit, he should still adjust his movement to grab this object, and also to react to errors in perception. And this is quite common, especially with arms that are not so accurate as ours. Then we also have navigation. Our navigation is based on the navigation stack of ROS adjusted to our robot. So we use move base, we use dynamic window approach, and for localization we use adaptive Monte Carlo localization that relies on laser scanners and the odometry, but also in the map that is pre-made to allow a localization and navigation. These methods allow for a multimodal navigation that for now we have 3 modes. We have the waypoint navigation, which is a normal, I want to go there, and we give them the coordinates and it goes there. Then we have the dynamic goal, which is a goal that moves with time. It can be anything. You can want to reach this goal exactly, or you can want to have a certain distance between you and this dynamic goal. And an example of this is people following, as you could see in the video. Since the people is a dynamic goal, then we also have a guiding mode, which is basically the robot has to reach a certain position, but it has to make sure the person follows it. So what we do is we move backwards, since we have omnidirectional wheels and lasers to see all around. So we move backwards and we keep the camera in the front of the robot, tracking the person, and we calculate the distance to this person, and we try to maintain this distance always under a certain threshold. Then we have finally the task planning. The task planning is what fuses all the components into what allows to solve a certain problem. First of all, we have the basic actions of the robots, since navigation to a certain point or pick this object. Of course, there's conditions that have to be met, but these basic actions are built in a Python class that we call mbot class. So every single thing that the robot can do in its more basic state, it's in this class. Then we build states or to do something, like perceive this table is a state, and the robot has to use its actions to go to the table, look at the table, detect. So states are built with actions, and then we build state machines that are built with these states to form the whole plan that is more or less linear, but it also has to depend on what the robot did before and what it perceived before and what it is perceiving now and what is its goal. In this video, we can see the robot performing the challenge in Milton Keynes. So the robot is supposed to be a waiter. It's going from table to table to check if it's empty, if it has objects that need to be cleaned, if it has people and no objects, so that this person needs to be served. And if there are people with objects, then it's okay, they are already served. And then he should go to the person who doesn't have any objects and serve them. So if we move forward a bit, he's still checking tables. Then he moves to the person that didn't have any object. He communicates with this person to ask what they want. In this case, we use the tablet as an interface if the speech fails, and then the robot will grab the food and bring to this person. Now, some best practices and lessons learned I've learned over my experience, and also that were taught to me. So first of all, you should have a solid foundation. Before you start implementing anything new that you want to build, you should first build something with what already exists. So as you can see in this scheme, we can, and I spoke about this before, but we can more or less divide the robot system in these main components, such as the speech understanding, object perception, navigation, manipulation, task planning, and all of these components have a lot of research done about them, and there's a lot of public available packages that do this. So you should start with those, adapt to your robot, and build a solid working foundation that works very well and it's robust. And after that, you can apply your research to one of these components. You can even replace all of them, but always having this solid foundation to go back to. If anything you do gives you problems and you don't have time to fix it, you could go back to this working backup, and it will help you to be more resilient. And besides building a robot, you are also building a team. You might not get to choose the people you want. You might not have the right number you plan to, but you have to work with what you have, and to have the best team possible, they should have a good relationship between them, because usually people work better in a good environment, and also it helps when they have problems that need to be that need someone to help them. So if I have a problem and I know my team members, their weaknesses, their strengths, I know who to ask about this certain problem, and then it's also easy for me to ask them for help, since I know them well. You can also do, of course, some team building exercises, but that's a bonus. Then a good habit that I learned from previous team leaders are regular meetings. These meetings can be held once a week or once every 2 weeks, but they are very good, so everyone is aware of everyone's progress, and so that everyone has a global view of the state of the robot, what is already done, what needs to be done for the next competition. And it also is very helpful to discuss problems. So if someone has a problem that they are having problems solve, they can come to these meetings and discuss these problems, and everyone gives their insights, their ideas, and it might be easier for them to solve after discussing this problem with your team. These meetings can also be held in robot competitions. In these competitions, usually people are very stressed out and they just want to finish their tasks, but if you take a bit of time, join everyone together and talk about what is going well, what is not going well, what needs to be fixed, what is the approach for the next trial. It helps bringing everyone to the same page, and this drastically increases the probability of success that you will have. As for the work assignment, you should divide the work that needs to be done in several components. You should prioritize these components as well, and then assign each one to a single person. If they are responsible for a component, they feel like it's their job to have this component working well during the competition, and this increases the probability of everything working well during the competition. You should also try to have more than a member working in each component, so that if someone gets sick or if they cannot work, something goes wrong, there's always someone that can fix any problem that might arise, and it increases the probability of success of your team. Then every competition has a rule book. You should read this rule book very well, so you don't lose any points in an uncalled way. So if there's a rule that says specifically you cannot do this, and you do that because you didn't read this, it's a waste of points. So read the rule book well. If you have any question, you can ask the organization. They want to have a good competition with good results, so if they can, they will answer you. Then you should brief everyone about the rules, the most general rules, and then you can ask them to read the rules that are more specific for their job in the team. Of course, if everyone reads everything, it also works. After the rule book, there's also the description of the tasks that you need to perform. I personally like to read these tasks, and list what the robot needs to be able to do to achieve these tasks. Then after I have this list, I can check each one of them to see which one the team has already working well, which ones we have but are not working as well as we want to, so they need improvement, and which one we don't have at all, and then we need to work harder on those ones. This means you have to prioritize your work on what you have working and not working, and assign, like I said before, to every person. And then you can see in this table we have several components that we need to have working when the competition arises, and people assigned, and the status, if it is okay, if it needs work, or if it's not working at all. And tasks that need more work are, of course, the ones that we don't have anything. So in this case, manipulation should be very worked on, so that when we get to the competition, this part is working and we can actually perform the task. Then you should also double check what is working. In the previous case, you thought, oh, okay, so human-robot interaction is working very well, so it's okay. Double check that. Something might have happened in the meantime. You should also recheck after every hardware change. When you're changing something, you might accidentally unplug something, or just touch a cable and it gets loose, and then something goes either broken or it just stops working because it's unplugged. When you move in hardware, it's always risk prone, so you should recheck your code after these hardware changes. You should also recheck after you implement an upgrade to something, and usually everything has dependencies. So if you upgrade a code and it's working fine isolated, you should also check its dependencies because they might go wrong. And when you implement something new and you want to integrate it, this is also a good time to check everything, because these integrations are usually very workful, and they can bring problems. So especially before you go to competitions, if you are integrating something new, leave some time to test, because something might go wrong. When you are structuring software, you should not only structure your code, you should structure that, but you also should structure the way your package is built, where each file is, and how it is built, what is the directories organization, because this is very important. For example, if you have a robot directory, you should have the main components in this directory, and then in each of those directories you should have the subsystems that are related to it. And you should also focus on the names of the package, the nodes, the topics. You should give a good name to each thing, so it's intuitive to know what that node, topic, package does. This is very important, not only for you and your team members, but especially for the future generations. In long-term projects, the teams always renew, so new members come in and they land on a project that has a lot of programs, a lot of packages, and if it's intuitive to know where things are and what they do, it's better for them to be integrated. It also helps them if you have proper documentation. Not only the code is documented, which should always be done, but also each package, how it works, how it is built, what are the inputs, what are the outputs. This should all be documented in a proper way. And there should be always also a tutorial for how to change things that are expected to be changed. I can give you an example. For example, our specific detector has to be retrained every competition. So we need a tutorial on how to do it. So even if someone doesn't know how the specific detector works, or how this neural network is working, they know how to record the image, label them, put the neural network training. So we have always a specific detector easily built. These tutorials are important. so new members know how to do these things that they need to do. Imagine that the whole team is renovated and no one is there to give you the heads up on how these things work. If it's well documented, you don't need anyone. Then you should always try to have your code accident proof. And what I have for this is basically have your code in a safe place. So save what you really use and the stable version in a separate repository or branch. And then in our case, we have in a repository, then we fork this repository for every team member. They work in their fork. So if I'm working in my fork, I have a local repository of my fork. I work in it. I pull and push to my repository, to my fork repository online. And when I think my code is ready to be integrated into the main repository for everyone to use and to be used by the robot, I do a merge request, which will be reviewed by several people. And this gives 2 extra security layers for each code that is new to the repository. And you should you might also have the question, should I commit? This usually arises when you're in the middle of your code. And usually my answer is yes, you don't lose anything. It helps you to store every step of your work in a safe way. So if something goes wrong close to the end and you had something that was working well before, you can go back to those versions. If you only commit in the end of your work, it might happen that you are working on the robot, for example. You implement your code, you don't commit it, and then someone needs to use the robot, uses it, and by accident erases all your code, and you have to start months of code all over again. This happened to a previous team member, so you should always commit your work as you progress. So there's always a safe and a safe backup, let's say. There's always a safe backup of your work in every step. You should also not be lazy in your commit messages, because they are important not only to you, because now you know what you are doing, but in the future you might not know what you were doing at that time. So if you just write update on the code, you don't know what this is. So focus on these commits, write something that will help not only you, but the people who use your code, so they know what this commit brings new to your code. Another good point is that organization is very important. You should plan when you are in with a lot of time restraints. Time is a very valuable resource, especially in robot competitions. So if you go to a competition, you should plan what needs to be done, what are the dependencies on each activity, and what are the time constraints. If you use a tool or an online tool, everyone has access to these plans, that you can see what they need to do, how much time they have to do it, and how this influences other people's work. And when assigning time to these tasks, you should always be realistic. So if a task should last 2 hours, don't assign 3 hours, or it will take those 3 hours. This is called the Parkinson's law, that this law says that the task will expand its work to take all the time that it has available. So you should give realistic times, and then save a spare time for any errors or any accidents that might happen during the task execution. If they get late, you have always this cushion of time, but leave it private and in the end, so it's not it doesn't influence each task. This is especially useful in setup days when time is really very restrict, and a good plan will help you in accomplish a good setup. In terms of what you can take, you should always take as many spares as you can. If you can afford it, and if you can take it with you, go ahead. You should focus on the parts that give you more problems. If you have a certain part that is known for giving you problems and is always breaking, focus on taking a spare for that one. This is the basic Murphy's Law. If something can go wrong, it will. I remember when we went to Milton Keynes, we were packing and we had 2 chargers, and our charger had never broken down, so we didn't have to take the second one, but we had space and we had that charger, so we took both. During the competition, we were going to charge the robot one day and it was not charging. The problem was the charger. We could not fix it, so we just replaced the charger, and it all worked out. It all worked out well. What ended up to be just a simple switch could have been the reason why we had to forfeit the whole competition. So if you can take something, go ahead. It might be needed. A case where a second of something was useful for us, and it was not a part; it was a whole team. In the RoboCup in Montreal in, I think, 2018, we had a lot of team members. So we divided the team in 2. Some members went to Montreal with a robot, some stayed in Lisbon with another robot, and due to the time zone difference and the 2 teams, we could be working 24 hours in a day, a team in the place doing the competition, solving problems there, and a team working in Lisbon to solve any problem that could be solved by distance. This helped a lot because it basically meant we had twice the manpower to solve the problem. So if you have spare team members, use them. It's also important, before you pack the robot, to list everything you need to take. Not only list what you need to take, but also take photos and record the serial numbers. This will be important. Of course, you need to be careful with what you can take in terms of volume and weight. Also, you should check with the persons that actually need to take a lot of things, which is usually the person responsible for the hardware, because they need tools. They know better which spares you need to take. And the reason why you should record the serial numbers and the photos and everything very accurately is because if you change countries and you have to go through customs, usually they need a specific list of objects that you will take. When we went to Abu Dhabi, we packed the robot and we sent it. But when we were packing, we had to put some things at the last hour and we forgot to put it on the list. And then when the robot got to the customs, the people there stopped because there were things that were not listed. So we had to go there and pack the whole box, bring the robot outside, check everything. And this was very stressful. It gave us a lot of work and it consumed a lot of time. So do this well, so you save all this trouble in customs. You should also double check your packing. When you're packing, you should, of course, wrap things well. Use a lot of bubble wrap. You should use cushions if you have to. Just make sure nothing breaks when it's traveling. Should also check if everything is in the box. You might forget something. It's very easy. And if you should also check if the robot is working properly before it is shipped. So before we went to Abu Dhabi, we checked if the robot was working, but the arm was not working. So we checked what was going on. We took some hours, maybe, I don't know, 6 or 8 hours, and it ended up to be a blown up fuse in a circuit board. It was very tiny. It was hard to see. But we detected the error. We fixed it, and then we sent the robot. Imagine if we got to the place with our robot, this happened, and we would lose 6 to 8 hours of work in the setup days, where we only had 2 days or 3 days. It's a lot of time that can be prevented by checking if everything is working before you ship the robot. Then you get to the competition, and then you have the setup days. These days are very stressful. You will not be the only team that wants to set up. You will have problems. Probably, maybe not. If you don't, be thankful. But usually people have problems, and you should especially use well the time that you have allotted in each arena. So usually these arenas have time allotted for each team. Use well your time, because if you are planning to use a time that is not allotted to any team, the other teams will also want to use it. As you can see in this image, every team was in the arena trying to set up, and there are some things that you cannot do when there's all other people there. Of course, a good plan helps. So if you have a good plan and everything goes more or less according to plan, you should be fine. Finally, I would like to talk a bit about the balance between research and the state of the art. So, of course, you should try to do research and innovate whenever you can, but you should also be practical with your time limits and your constraints. So if you don't have time to do a lot, you should aim to do something that you really want to do in the proper way. And if you do a nice research on a component and you show it in around the bulk of state-of-the-art components, this will be very good compared to trying to apply research all over the place, have everything new, but it's always breaking down, so you cannot show anything. So a good innovations in a few components around a nice bulk of state-of-the-art is a good solution. But you should also remember that winning is not everything. You should try to win. It's important, but most of all, the purpose of these competitions is to bring advancements in robotics, to apply research in fields that need it, and to solve problems that haven't been solved before. So you should aim to perform well, but you should not only use state-of-the-art things and do some hard code. You should actually try to be general when you can and apply some research, like I said, in some components that you think will be relevant. And of course, you should share your knowledge. If you will do your work and you don't share it with anyone, it will be basically useless. And you should know that knowledge generates knowledge. So if you share your knowledge, it might be the base to more breakthroughs, and it's always rewarding when people use what you had done. So share what you did, learn what other people did, so you can have new ideas. And this learning and interaction with other people, because these competitions are filled with interesting and very intelligent people in your field of studies or related areas. So talk with them, show them your work, learn from them, and have fun. I thank you. If you have any question, please ask me. And thank you for listening.
Hey, that was a really nice talk.
Thank
Thank
you.
you, Rui. So let's begin with the questions, maybe. So there are a couple of questions from the audience. But one thing I want to conclude. So one thing what I can understand from your talk, yes, there is a technical aspect of robotics, but what I see in participating in competitions, so you also have the logistics part, right? So it is this combination of both, which, because I see your presentation, it's a lot of time into logistics, right? So if you want to participate, you have to look into both the aspects. Right.
Yeah, sure. In my experience, is most of the problems are in logistics rather than actually technical part.
Oh, so you claim that you have solved all the problems. And
No,
only...
I don't claim that, but I hope my experience can help some people, so they don't.
So from my past experience, also I can say that logistics is and it's very nice to listen such experiences being shared and given such importance, because if you go to a research talk, it's all the pure core research, and these are the problems we solve every day. So let's start with the question. So one is it has been asked by Santosh. So he's there. So when you prepare for a competition, how much do you prepare beforehand, and how much preparation needs to be done on the competition side?
So basically, we start preparing as soon as we finish a competition and we know that we are competing in another one. We start the preparation, and we decide what we will do, what we will implement new, what we will keep, and then we work on it until the competition. We leave some time for testing, and then we go to the competition. Then we usually have more or less what we need to do planned. So we have step by step what we need to do.
Yep.
We follow those steps. Usually there's something wrong, but we fix
Yes.
it, and then we get in time to compete.
But that will be a nice question. So how well are you following your own plans? Because
Right now we don't have any competitions. It's like everything we had has been delayed. We maybe have something in November, but it's not confirmed yet. We are
Right.
preparing that, but
right. But don't forget, so next year there is the ScyRoc's next year Smart City
course.
competition. So it's in Bologna. So let's see. So we have
We'll see.
one more question. So I think we have time for that also. So it's from Mohammed Vasili. He has two questions actually. How do you integrate your code to different robot platforms? So since you showed, I think you have your MBot, and you also have your Mohammed, the robot who participated in the Mohammed bin League. So are you sharing your code platform between them?
Actually, we have two robots, but they are the same model, so it's the same robot platform.
Okay.
The other teams that work in other domains, we are not the same members, so the code is shared only if we talk with each other and we share ideas.
Okay.
But it's mostly separated.
Okay.
How do we deal with different ROS distribution?
Yeah, so this is an important question. So how do you deal with ROS? Because ROS is coming every year. We have the new distribution, and now we have the bigger change, right? So ROS 2. So are your plans ready for ROS 2 ready, or how is it going at SocRob?
So for now, we've been using ROS Kinetic for some time now. So
Correct.
that is been
Yeah, so
great
you're
for
happy.
us. We're
So-
very happy, but we have to change eventually because Python 2.7 is out of date.
right.
We have to change, but we are waiting a bit because both ROS Noetic and ROS 2 are a bit new, and some things are not that well supported yet. So
Okay.
we will see in time when we do the transition,
Good.
because it's a lot of work.
Yeah, so I think that's the intention of the question, because so every time you have to change your distribution,
Of course.
and now to ROS 2, it's a big effort. I think most of the teams are setting up a new student league for the transition. So I think it's time. Maybe I'll ask the last question from my side, so that and we might conclude this session. So the question what I have, since this camp is meant for new team members, right? So new teams to join in there. So what do you think? What do you think as a team member? What do you think anyone can gain? Like any student who wants to join the robotics team or want to start a robotics team. From a student side, what do you think is the most important factor?
Well, first of all, I think, for example, for students who are doing their thesis, it's very good for joining these kind of projects with teams and competitions, because they get to implement their research in actual case studies that are relevant.
Right.
Also, as a student, you get to work with people that are in the same level as you, but also in levels above. Like as a master student, you might work with PhD students, and you gain a lot of experience from their knowledge because they know a lot. And as a master student, I learned a lot from my PhD student colleagues. So
Yeah,
that's amazing.
nice. So I think that's it. I think with that positive remark, I think we can conclude our session. So thanks, Rui. It was really nice to have you and to share your experience with amongst us. I think I'm dead sure that in the community this will be taken as a positive step, and they will learn from your experiences. So thank you, Team SocRob, and thank you.
Thank
Bye-bye.
you. Good luck with the remaining talks.
Yeah, do that. Bye-bye.
Bye.
Bye. So everyone, we continue with our Champions Talk series. So we also have a second talk. So for our second talk, we have Team Pitbots. So the next talk is by Team Bitbots. So Team Bitbots is a robotics team from Hochschule Bonn-Rhein-Sieg, Germany, from the Masters of Autonomous Systems group. To a little bit fair, I'm also from the group, so I will be a little bit more interested. I'll be making a little bit more marketing about this. But let's start with the Team Bitbots. Also has a long history with robotics benchmarking. and participation in various robotics competitions. So they are participating in the robotics at work right from its inception in 2011. So they also participate in different European robotics league like Rockin, Rock EU2, and also now in SciRoc, same like the team SocRob. So, but the most important thing currently, they are the world champions. Yes, I'm very excited to have a world champion in our in this in the first talk of ScyRoc Camp. And also, they were also in the last year the ScyRoc competition winner for the pick and pack event. So, saying a lot about Team Bitbots, I'm very excited to learn from them, their experiences and approach, what led to their victory in this world championship. So also here the team was kind enough to give us a video of the format. But don't worry, after the talk, there are two members of the team who will be joining us, so we can ask any questions to the team members, and they will try to answer those questions in there. So I request all the audience to use this service if you want to ask the question. So there are two ways to ask the questions. As I said, you can ask in the YouTube comments, or you can check in the ScyRoc Camp website. There are places we can post your comments. Okay, so moving on to Team Bitbots. I think we are facing some streaming issues. I think we'll be on in a bit.
Hello everyone, my name is Santosh and I will start this presentation about our team's performance at the ScyRoc competition last year. So our team has participated in several competitions such as RoboCup at Work and other European Robotics League competitions since 2012. And today several members of our team will present different parts of our architecture, including navigation, manipulation, perception, and task planning. So we'll start by showing you a video of the robot performing the shopping pick and place episode at the ScyRoc competition last year. So the robot is given a task to pick up several objects from the shelf and deliver it to a box. So once it receives the task, it navigates to the shelves. It then perceives the shelf to detect the different objects and selects the object that it wants to pick. It transports the object then to the red box at the other end of the area. It then repeats this pick and place task several times until it has completed the task. Now, Raghuveer will present the hardware that we use on our robotics platform.
Thank you for the introduction, Santosh. We'll now talk about the robot platform and the associated hardware used by us during SciRoc 2019. We start off with a pictorial representation of our robot. Here on the left, you can find our robot platform in its entirety with the various components highlighted. On the right, you can find an expanded view of our robot's gripper assembly, showcasing the in-step camera between the two flexible fingers. In the forthcoming slides, we'll talk about these components and describe some of their specifications in brief. Let's get started with the robot platform. As is the case with most other teams in our league, we've based our implementation around the KUKA U-Bot. The standard KUKA U-Bot platform comes equipped with a 5 degree of freedom manipulator, an omnidirectional pace, as well as a 2-finger gripper. We've added a lightweight custom-designed aluminum backplate to the platform for easier storage and transportation of objects between workstations during competitions. We'll now focus our attention to the components that have either been added or upgraded on the existing standard platform. We begin with the computer. The standard internal computer that came along with the KUKA U-Bot has been upgraded to an 8th generation Intel NUC kit. This computer comprises of a Core i7 processor at its heart and 8 GB of RAM. Thanks to its small form factor, along with its lightweight design, we are able to interface our external devices and other peripherals on the robot platform without increasing the robot's weight itself. We'll now take a look at these components. We start with the laser rangefinders. For our implementation, we've made use of two Hokuyo URG04LX laser range scanners. These two range scanners are mounted vertically flipped at the front and back side of our platform. This allows our robot to navigate in both the forward and backward direction without colliding with the external environment or objects. Among other specifications, some of the key specifications for these range scanners include a scanning time of 100 milliseconds per scan, as well as a measuring area of 240 degrees. We now focus on the camera. The camera that we've used for our implementation is the Intel RealSense D435 depth camera. This is an RGBD camera, meaning it provides an RGB color image along with a 3D point cloud. The camera is fixed at the center of the gripper assembly, which is surrounded by the two gripper fingers. Thanks to its 30 Hz for RGB data and 90 Hz for depth point cloud streaming ability, we are able to achieve almost real time in our perception related tasks. And finally, we speak about the gripper assembly. The gripper themselves are made from a custom designed gripper fingers and are actuated by two Dynamixel AX12A servo motors. These motors provide position as well as force feedback information, which allows us to estimate whether the object to be grasped is actually correctly grasped or not. This was a brief introduction of our robot platform and hardware. And now I'll pass it over to my colleague Carlo, who will take us through the manipulation stage. Thank you.
Thank you, Raghuveer, for your introduction. Now I'll move to the manipulation section. This section, I've divided everything into two parts: the base manipulation framework and the velocity controller that we use for particular tasks. On each slide, you will see a, a graph. It's the pipeline for each of these processes, and I will try to move through each step and explaining it. For the base manipulation framework, we start with an input, which is the target n effector pose for grasping. This will come from the perception module. The n effector, and by the n effector, I mean the last link in the arm, where usually is the gripper. Now for the second step, we have the move it inverse kinematic solver, which is used to go from 3D space to joint space. Then we obtain some target joint angles that we can use with move it. Additionally, move it allows us to just give joint angles to move to predefined arm configurations if we want to. That's an option. Then we have a pre-grasp planner to find a suitable arm configuration to achieve prior to moving to the target and effector pose. Once we have a pre-grasp and a grasp joint configurations, we fed them into a motion planner to be executed in sequence. This motion planner was made by someone in our group and is an interpolation-based motion planner. We use it with MoveIt. So finally, we have a MoveIt sends arm commands to the arm. The arm moves to where we want it to be. So in the end, as output, we get a new arm configuration with the N effector at the target location. And once the N effector reaches the target location, it will send a message to the gripper. The gripper will close, trying to grasp the object. And then it will send some feedback for grasp verification to know if we actually grasp anything. Now we'll move to the velocity controller. The input for this controller is, again, a target and effector pose. But as I mentioned before, this controller is used for particular tasks. So what we do with this pose is we fed that into a custom node that we have, specific for each task. For example, curve tracing or just line tracing. And this node will calculate the desired linear velocity for the n effector. Now, we obtain the target velocities. Additionally, we can just fed a constant linear velocity as input if we just want to move along a line. Then we have an inverse kinematic solver for the velocities. So we can go from 3D space velocities to joint velocities, joint space velocities. So for this one, we used an weighted damped least square method from the Orocos KDL library. So finally, we obtain some target joint velocities, and this can be fed through the arm as commands. So finally, as output, we obtain a new arm configuration with the end effector moving towards a target location. Okay, that would be all for the manipulation section. Now Deepan will continue with the navigation section. Thank you.
Thank you, Carlo. Hi, I'm Deepan Chakravarti Padmanabhan, and I'll be presenting the navigation stack to you. Navigation includes mapping, localization, path planning, and motion control. So first, we'll see mapping and localization. Mapping is done using Gmapping ROS package and the laser scanners from Hokoyu laser scanner. The map is generated in the form of 2D occupancy grid, where the white area shows the free space, the gray is the unknown area, and the black is the occupied area. In SciRoc competition, since we know the positions in which the robot is navigating, all these known positions were already added to the map. The next is localization. In order to get the robot pose in the map, we use adaptive Monte Carlo localization, the ROS AMCL package. The next is MoveBase. MoveBase is primarily used for path planning and motion control. It includes the global and local planner. The global planner is used to get the shortest path between the start position and the goal post, and the local planner is used to provide the velocities in between the paths, and it also helps to avoid the obstacles. And the recovery mechanism which we have, it includes clearance of the cost map in the beginning, and it is followed by force field recovery. So we'll see them in the upcoming slides in a detailed manner. The next is global planner. We use ROS global planner package, and the shortest path to the goal post is generated using the A-star algorithm. And the robot doesn't follow a pure omnidirectional motion. The robot initially follows an omnidirectional motion to align with the path. After aligning with the path, it proceeds using differential drive motion, and at the end, again to align with the goal post, it does omnidirectional motion. So this is helpful, and it provides us the capability to look as much as possible in the forward, and this is especially helpful to avoid the barrier tips in artwork competitions, artwork lab competitions. And the next is it also provides you additional capabilities, and it eases you the navigation in more narrower passages. And the next is local planner. So the local planner that we use is ROS DWA local planner. So it is a dynamic window approach. So it samples velocities from the robot control space, and it forward simulates various trajectories for the robot, and the trajectories which are colliding with the obstacles are avoided, and the remaining trajectories are scored depending on various criteria. A few are like how proximity it is to the goal post at the end of the trajectory, or how close it is to the global path planning, and how close it is to an obstacle. And all these criteria will be used to score each trajectories, and the best trajectory is chosen, and the velocities are, and the corresponding velocities are provided to the robot. And the next is the force field recovery. Force field recovery is used in places where the robot is stuck, like if it is not able to generate a motion, or it is not able to, or it is moving in between 2 points in a repeated way for a extended period of time. So in those cases, we use force field recovery, which is developed by SmartLab. So what it does is, within a defined radius from the robot, it looks into the occupancy grid, and each cell that is occupied in the occupancy grid exerts a force to the center of the robot, So the resultant force is calculated, and it is used to provide the wheel velocities. The wheel velocities are provided for a shorter amount of time until the robot is overcoming that scenario where it is stuck. And the next is um, we have used only the standard ROS packages from the DWA or the AMCL packages. So in order to make them work in a better way, we tuned the parameters, and you can find the values of those parameters in the link provided. And the next is direct base control. So at some scenarios, it is necessary to provide some relative motion uh, to the robot. Like after we go to the service area, after perceiving, the robot has to align in a particular way to the robot so that it pick is more efficient. So we see the relative pose error using the target pose that we have already generated, and the AMCL or through odometry we find the relative pose error, and this relative pose is being provided to the robot at the end. So like it would be like move 20 centimeters to the left, or a particular orientations. And this is why we use direct base control. And during this motion, the collision avoidance, it is done using the laser scanners. And yeah, that's it from navigation. And thank you so much, and over to Heruka for perception.
Thank you, Deepan. Hello, I'm Heruka, and I will describe our perception pipeline. In the competition setting as seen here, each shelf contained only one type of object, and the type of object at each shelf was known before a competition run. The objective was therefore only to obtain the position of an item on the shelf, and object recognition was not required. Therefore, we took a very simplistic approach using only the point cloud data from an Intel RailSense D435 camera attached on the end effector of the robot arm. Since the field of view of the camera was insufficient to capture the entire shelf top at close proximity, the first step was to combine multiple point clouds recorded from different viewpoints to create a complete point cloud of the shelf top. This was done by creating a sweeping motion with the robot arm, as seen in this video, transforming each point cloud to the baselink frame of the robot and accumulating them in an octree data structure. A downsample point cloud of the shelf top with a voxel size of 5 mm was then obtained from this octree. The next step was to identify the area which corresponds to the top surface of the shelf. This was done through ransack-based plane fitting on the accumulated point cloud to find the most dominant plane equation, which is more or less perpendicular to the z-axis. Once the plane equation is obtained, all points which are close to the plane were then projected onto it, as seen in red here, and the convex hull of these inlier points were then extracted, as shown by the blue cubes. The convex hull points are then shifted along the z-axis to create a polygonal prism, and the outlier points from the previous plane fitting step, which lie inside this polygonal prism, are extracted as object points, which as shown in green. In the final step, the extracted points are then clustered based on the Euclidean distance between points, and the object with the nearest cluster centroid is then selected to be picked up by the robot. Once an object is picked up, it is staged on the back platform of the robot during transportation. In order to ensure the object was in fact placed on the back platform and has not fallen down in the process, we perform a similar set of steps as explained with the object detection to detect that the object is in fact on the back platform. Similarly, we also do this check after unstaging an object. If the object still remains after the first unstaging attempt, we perform a PCA on these object points to obtain the pose of the object and reattempt unstaging with this new pose. Although it was not required in the competition, oftentimes it's necessary to identify the class of the object. For this, we take the cluster point clouds from the previous step and first extract the 3D modified Fisher vector, which provides 540 features. We also slice the point clouds 8 times along each principal axis with even spacing and extract the radial density distribution features of each slice, which provides an additional 24 features. The objects corresponding to each point cloud cluster was then classified based on these combined 564 features using a random forest classifier. In scenarios where the objects don't have unique shapes, we also utilize image-based object detection and classification using the squeeze depth network. To get the 3D pose of the detected objects, we extract the 3D point clouds corresponding to the pixels inside the bounding boxes and get the object orientation using PCA after removing the points corresponding to the workspace top. A final list of object poses and classifications are then obtained based on the class probabilities from 2D and 3D classification, as well as any prior knowledge, such as the type of objects that are available on the workspace and the classification accuracies of certain objects. That concludes the explanation of the perception pipeline, and I will now pass it on to Damin to explain task planning. Thank you.
Thank you, Haruka. Hello, everyone. My name is Dharmin, and I would like to talk about task planning. Let's take an overview of the task planning. The task is provided by RefBox. This task needs to be executed by the robot. On the robot, we have a RefBox parser. The parser interprets the task given by the RefBox and adds the goals according to the task to the knowledge base. What is a knowledge base? Knowledge base is just a database which stores instances, facts, and goals about the environment and the task that needs to be done. The knowledge base is used by problem generator to generate a problem file. This problem file, along with domain, will be used by a planner to solve this problem. That will generate a plan file. This plan file is now used by planner executor that executes individual actions using 7 actions state machines. The state machine, as you can see on the slide, are move base, stage, unstage, etc. So what happens when an action fails? When an action fails, the planner executor realizes this and replans. So it sends a request to the knowledge base, updating all the knowledge that is now static in the environment, and then that is used by problem generator to generate a new problem file. The planner then uses this new problem file to generate new plan, and the cycle continues until all the actions are successfully executed. So let us see what we did in SciRoc. We had a pick and place task. A simple problem of pick and place can look like this. A problem file has all the knowledge needed to create a plan. So here you can see that our problem file has objects, like the objects that are in the environment, and the location, for example, nuts and bolts, locations such as workstation 1, 2, etc. It has an initial state written here as init. This stores the information of where the object is at the moment. It also has a desired state written here as goal. This desired state is what is required to be the case at the end of the task. Given this problem, how does a planner know which action to take? Here, for example, I'm showing a pick action. You can see that in preconditions, if an action needs to be taken, some conditions needs to be satisfied first. For example, the pick action requires the workstation that you're picking from to be perceived first, and the gripper should be open. Alongside that, there's effects that needs to be taken care of in the action. Effect is all the instances and fact that will be true once an action is successful. This will change the knowledge base since it changes the environment. Now, how does a robot know what is the state of the environment? This is taken care by knowledge base. A knowledge base contains instances and facts about the environment. For example, a knowledge base can contain object phi is on workstation 2, robot is at workstation 3. It can also contain goals, such as object phi should be on workstation 1, robot should be at workstation 5 at the end of the task. As you can see here on the right, the image shows an immediate plan that needs to be executed along with all the knowledge from the knowledge base. You can see on the workstation, the objects are present that needs to be picked, that are shown in blue. The objects that needs to be placed, that are shown in green, and the objects that do not need to be interacted with. The image also shows a plan action that needs to be carried out. For example, here, a move-based action needs to be carried out, which is shown with the green arc. But how does a plan look like to the robot? A plan generated by a planner is generally a text file with each line containing a single action. Example, a pick should be performed by a robot U-bot BRSU, and it should be picking up a bearing 00 from a workstation 03. Now let's take a look at the visualization of the plan being executed.
Here you see that the green arrows are move-based actions, the blue is the place action, and the green objects are supposed to be picked by the robot.
That's it for planning. Now I'll let Ishwarya talk about our architecture. Thank you.
Thank you, Dharmin, for your insights on planning. Hello, everyone. I'm Aishwarya, and I'm going to talk about the software architecture and development. Up till now, we have discussed about different components such as navigation, planning, perception. Right now, we are going to see how these components are organized, put together, interact, and how they work together. So let's start with the software architecture. So as you can see from the diagram, we have a layered software architecture. So at the lowest level of this architecture are the lower level components or the ROS nodes. So the ROS nodes are aimed at performing a domain-specific task, such as a task related to perception, navigation, manipulation, and so on. So these ROS nodes are then managed by the higher level actions. So the higher level actions are aimed at performing one specific task, such as picking an object, placing an object, moving the base of the robot, or even perceiving the robot's location. So the higher level actions are generated as a part of the plan by the planner. So the planner is on the top level module, and the planner generates a plan. A plan is nothing but a sequence of actions, and these sequence of actions are executed using the state machine. Let's now have a closer look at each of these layers. So on the top is the planner, and we use the Llama planner in order to generate a plan for a given task in the competition. So the plan is nothing but a set of actions or a sequence of actions. So the sequence of actions are something like as shown in the top figure, such as move base action is followed by the perceive action, followed by pick object, followed by stage object. So this is an example of a simple plan to pick up an object. So these actions are then wrapped together and executed as a sequence using SNAC state machines. So each action now has a set of states, and the state machine executes these states in sequence. So the diagram below now shows a sequence of states in order to execute the pick object action. So the sequence of states starts with the object selector state, where the object to be picked is selected by the perception module. And then this is followed by open gripper, and then the gripper grasps the object, and then the gripper closes, and then the grasped object is verified. So if all of these states are executed successfully, then the state returns with a success message. And if there's a failure in any of these states, then we return with a failure message. So now each of these states call different ROS nodes in order to execute the required action. So each of these ROS nodes use ROS topics for communication, and these ROS nodes over here are standardized by using the event in and the event out topic. We use ROS topics because they provide a non-blocking means of communication. So in the case of the event in topic, the user of the state machine publishes a start or a stop message to the topic, which in turn is subscribed by the nodes, and this then starts or stops the respective nodes. The case is reversed in the case of the event out topic, where each node publishes its execution status to the event out topic. And then the user or the state machine can then subscribe to this topic in order to find out the execution status of the node. So this is all about our software architecture. So let's now have a look at the different packages which are used by our Bitbot software. So a Bitbot software has several packages, and these packages can be semantically grouped into the following categories. So the first is the UBOT packages. So the UBOT packages contain the necessary software in order to interact with the hardware. So these packages, software packages, form an interface between the software and the hardware. Then we have the planning packages. So the planning packages consist of planners, the open source planners such as the Llama planner or the Mercury planner, and these planners are used within the ROS-Plan framework. The manipulation packages consist of the open source Oroco's KDL for implementing forward and inverse kinematics, while we also have our own UBOT manipulation and MAS common robotics packages which customize some of the forward and inverse kinematic behavior. All the perception packages reside inside MAS perception, while all the navigation packages reside inside MAS navigation. So now we have software packages which are a combination of open source and natively developed packages. The natively developed packages are the ones which start with MAS or UBOT. So these packages are present as GitHub repositories, so they are hosted as individual repositories in GitHub. And all of these repositories or all the components in these repositories are then integrated into the MAS industrial repository. The MAS industrial repository is our main deployment pipeline repository. So this repository combines various components in order to accomplish the tasks in the competition. So all of these repositories along with the MAS industrial repository are cloned together, built and tested and finally deployed on the robot. So the deployment, the building, testing and deployment process is relatively complicated because of the huge number of software repositories which are involved. In order to make this process easier and to standardize this process, we have a CI/CD workflow. So a software development process follows this CI/CD workflow where we have the developers at the beginning who start with the software development process, push their changes to GitHub, and then in GitHub we have a continuous integration server which is Travis CI integrated. So this continuous integration server is responsible for building, testing, and deploying the code in a packaged format into a container registry which is Docker Hub. So the containerized images are then used for either development or for production in the case of continuous deployment. So let's now have a closer look at each of these steps. So the first step is continuous integration. So the continuous integration steps start with software developers working with the software using different code editors. So these software developers now develop code within Docker containers. So the Docker container based software development procedure is used over here in order to make the software development process agnostic to the underlying operating system. So once a feature has been developed, a pull request is made to the main repository in GitHub. The pull request then triggers a set of builds and tests which is carried out in Travis CI, which is our continuous integration server. Once these tests have been passed, the pull requests are merged, and once again the master are merged to the master branch, and the code in the master branch is once again built and tested in Travis CI. The documentation is built, and finally the code is packaged and containerized and pushed to a container registry. So the key highlights of our continuous integration step is that we use pre-commit hooks which perform automated quality checks on our code. For example, it checks for linting errors or even performs some kind of static code analysis. So pre-commit hooks, with pre-commit hooks, users cannot commit code unless all the tests have been passed. Similarly, integration tests and Catkin build are carried out in Travis CI for each commit made by the software developer. So once these commits have passed the test and they are merged to the master branch, the documentation is also built, and the documentation is generated using Sphinx in our case and then hosted on Read the Docs. Finally, once all the tests have been passed and the documentation is generated, the code is packaged and deployed as a container to a container registry, which is Docker Hub. So in a container registry Docker Hub, we now have two kinds of images. One is the development image and other is the production image. So the development image provides a development environment for software developers, and it is used by software developers to develop software. The production image is then used for continuous deployment on the robot. So the development image is a relatively lightweight software development, and it provides a lightweight software development environment, while the production image is packaged with the latest version of our code, and it can even be used by anyone who wants to run a demo version of our software. So these two Docker images now support running of ROS nodes, visualizers, and even gazebo simulations from within the Docker containers. So the final step of the CI/CD workflow is continuous deployment, where the production image is pulled, the latest production image is pulled from the Docker Hub, and then it is deployed on the robot. So continuous deployment is still in planning phase, and we are aiming to implement Docker Compose-based or Kubernetes-based solutions. Yeah, so with this, I would like to conclude my presentation. Thank you.
Thank you, Aishwarya. I would like to conclude the presentation by going over some points which are useful for us to manage our code base and our team. So in a student-based team, it is very common for students to join and leave the team every 1 or 2 years. So it is very important that the code that they develop is taken over by the new members. So we do this by writing tutorials and documentation for all the code that we develop. But one of the most effective ways for us has been to pair up new team members with the existing team members whenever they work on the robot. The second point is regarding our architecture. So in most of our components, we make them very easy to configure for different tasks. So for example, in the SciRoc competition for the perception, we only needed to detect objects and not recognize them. So it was easy for us to remove the recognition part from the pipeline, but leave everything else the same and without too much work. In most of the competitions that we participate in, pick and place is the basic task, but each of the competitions have slightly different requirements, which we need to then adapt to at the competition. So by having this flexible architecture, it makes it easier and less time consuming for us to do this. Thank you. And if you have any questions, you can ask them now.
So that was a wonderful talk. Thank you, Team Bitbots. So as promised, there are two team members who are joining us today. So we have Raghuveer and Ishwarya. Hi.
Hi, Deepu.
Hey, Deepu.
I think I'm missing in the screen. So I'll adjust myself. Hi. So first of all, thank you and welcome to the SciRoc camp.
Thank you.
Thank you.
And it was really informative and the effort from the team to put this presentation, and we really enjoyed it. So to begin with the questions, I think, so what I wanted to, maybe I can ask some questions which I wanted to ask was, so how is the composition of the team? Because I saw things, so are there bachelor's, master's, PhD students, so it's not mentioned in the slide. So how is the composition of the team? Maybe Raghuveer.
Yeah, well, our team is composed of bachelor's, master's, as well as PhD students. The majority of the contribution comes from students enrolled in Masters of Autonomous Systems course.
Okay, nice. So what do we learn in this master, and how is it related to robotics? Aishwarya?
So the MAS course is a coursework master's program in English, and it's one of the first courses in autonomous systems in Germany. So in this course, we study a lot about artificial intelligence, autonomous mobile robots, software development related to robotics, and similar courses. Most of our course work is related to research. So I would say that almost 50% of our credits comes from our research work.
So how does Robocop fit inside this research or this robotics working for you people? So do you do your research in the thing, or is it, so are you do for your coursework, or do you do it for fun? So how is it? Ishwarya, maybe.
So there are several features which we develop for RoboCup, and these features are very meticulously planned and implemented by students as a part of their research and development project or even their master thesis. Apart from this, we also have some courses, and as a part of this course, we are supposed to do some projects, and these projects might even be to implement certain bug fixes or some small features for RoboCup.
Nice. So Ravi, you talked about hardware. So I was thinking, so what other? So you talked about the U-bot hardware. So is that the only hardware you people work upon?
No, we also have another team here at our university that participates in the home league of RoboCup. So over there, that team participates with the Toyota HSR, or the Human Support Robot Platform. In addition to that, we also have a custom designed robot platform called the Robot, which was designed and built as part of an EU project of the same name.
Okay, nice. This is one question which I saw in the team SocRob, and maybe so. How is the team communication? So when do you people meet? What all tools are you using? And especially in this Corona times, how is it handling? Maybe
So yeah, so we have regular meetings on Friday. So before Corona, we had regular meetings at the university where we all get together. We discuss about what features are being planned, what we want to implement, what are the bug fixes. So we note them down, and then we put them as GitHub issues so that they're recorded, and specific team members are assigned to these issues. And these are the team members who are interested in these topics. Apart from this, we also have several online communication channels such as Slack, where any team member can reach out to anyone else and ask for help. Apart from this, students also come to the university and work on the robot, test their feature. But because of Corona, right now this is not possible. So our Friday in-person meetings have now been moved to online meeting, either in Zoom or WebEx.
Yeah, it's okay. So the team is still continuing in this time. That's good to know.
Yes, very much. Yes.
So one of the questions which was asked to Team SocRob maybe puts in there, and maybe since Aishwarya was talking about it. So how is the porting now? So do you still in ROS 1, or do you have plans for ROS 2? Or how is it planned?
So right now we're still in ROS 1. So our kinetic branch is stable, and this is what we use for the competitions. But then we have started the development for the melodic branch 1.5 years ago, and that is still in development. But now we have also started our new development towards ROS Novetic and ROS 2 also.
Wonderful. So you are moving towards things and plans. I think that's most of the questions which I had from the audience. I think it's nice to have you. So finally, I would like to thank, let me remember the team members. So it was Raghuveer, Carlo, Dharmin, Deepan, Heruka, and finally Aishwarya. So thank you all. Thank you all to the team members. Bye-bye.
Thank you. Bye.
See you. So that's team Bitbots for us. But that's not the end of it. You know, it's just we have started the week. This was the first day in a week with the Campions talk. So what do we have in for the whole week's planned? So that's the whole week plan we have here. So in the SciRoc camp, we will be joining tomorrow with the robot perception tutorial from Mohammed Bazil. It's the same time, it's at 2 o'clock. So all you people who are interested in understanding how perception works in robots, in robotics, and how it's been applied in real world, from the research, what is being applied in the real world, I think it's a good place to start with. Also, do check out the symposium, which is running in parallel. It runs at 10 in the morning. Tomorrow at 10, we have Itsuki Noda joining us, who would be speaking in the symposium, the Gerhard Kretschmer symposium. So finally, that's it from me today. So see you tomorrow. Ciao. Bye-bye.